We will focus on three types of atomic orbital overlap. They are SS overlap, SP overlap and PP overlap. When we study about overlap of SS, SP and PP orbitals, basically in organic chemistry, especially when we study about carbon, carbon has only S and P orbitals. So, that is the reason in this session and the remaining few other sessions, when we focus on molecular orbital theory, we will be mainly focusing on S and P orbitals only. So, this overlap may occur by head on or end to end or axial overlap. So, these are all the various types of overlap. We will be looking at each one separately. The first one is SS overlap. So, this is a constructive overlap. We can say constructive overlap is similar to addition. Two s orbitals combine together to give the sigma bonding orbitals as shown here. This results in lowering of energy of the molecular orbitals. In simple terms, you can visualize like this: when atomic orbitals mix, the volume of space available for the electron to move increases. This increases stability. In other words, energy decreases. Whenever there is a increase in stability, that is actually leading to decrease in the energy. So, the s orbital being spherical in shape, it can be aligned with respect to either x, y or z axis. It does not matter which axis we are considering as the bonding or principal or reference axis. The minion asks a question: sir, when two spheres combine, we are supposed to get a bigger sphere, but why are we getting a shape that is similar to an ellipse? Yeah, it is a good observation. In order to understand this, we need to look at the s orbital little carefully. When we say atom, we are focusing mainly on the electron and we are not focusing on the nucleus. Due to Born-Oppenheimer approximation, we assume that the nucleus is too big and does not move when the atomic orbitals mix. We do not show the nucleus. That is okay as long as mathematical calculations are concerned, but in reality nucleus does exist. So, the spherical shape of the s orbital is the place where there is a maximum probability of finding an electron. When two atomic orbitals interact, they are both attractive and repulsive forces operating. Electron in the first atom is attracted by the nucleus of the second atom and vice versa. Similarly, there is repulsion among electrons and among nuclei. Moreover, the nuclei are not overlapping onto one another when atomic orbitals mix. The two interacting nuclei are present at a distance which is the bond length. When you combine two spheres, that is s atomic orbitals having center is, that is the nucleus, which does not move or mix together, we end up in the elongated sphere or an ellipse. So, that is the reason we actually see an ellipse like structure and not a bigger sphere. If we speak mathematically, sphere has one focal point and the ellipse has two focal points, which exactly matches with the nucleus of both atomic and molecular orbitals. For bonding to occur, plus sign of the atomic orbital or the lobe interacts with another atomic orbital of the same sign. If it is s orbital, we take the entire sphere, and if it is p or d orbitals, we talk about lobes. So, here you see two lobes, one is transparent, another one is shaded. The reason why they are shown differently is to depict the positive and the negative sign or phase of wave function. So, when we say plus and minus, the sign here refers to the wave functions of the phase of the wave functions and not plus and minus charges. So, you have to remember this all the time when we talk about orbitals. What we mean plus and minus sign is only with reference to the phases and not the charges. So, do not get confused with the charge of the electron which is negative or minus. So, do not think that negative lobe will have electrons and the positive lobe has no electron. So, this is incorrect. Electrons can be present in both the lobes. So, this is simply the wave function's two phases, plus and minus phases, are represented like this different shades. This is nothing to do with charges, and this also has nothing to do with electrons charge. So, let us look at the S and P overlap. Here the S orbital is spherical, in other words it has no orientation. So, the deciding factor is the orientation of the P orbital only. For our reference, we can say we can use any P orbitals, and in this particular case let us take Pz as the interacting orbital. It is shown here. The S and P orbitals combine together to form the sigma bonding orbital as shown here. When we talk about S and P overlap, we have to pay attention to the bonding or the reference axis, because there are three types of degenerate P orbitals, orthogonals or perpendicular to each other, out of which only one interaction leads to sigma bonding and the other two are non-bonding interactions. So, when we say bonding overlap, we need to consider the appropriate axis for S orbital and P orbital. Since P orbitals are degenerate, we can choose any one as our bonding or reference or the principal axis, and mostly people prefer to take the Z axis as the bonding axis when we talk about S and P overlap. Let us say I take the Z axis as the bonding axis, and let us look at the symmetry of this P orbitals. This picture depicts the P orbitals. This is symmetric with respect to the rotation about the bonding axis. So, the constructive overlap leads to bonding orbital as shown here. Since the other P orbitals Px and Py are perpendicular to this Pz orbital, there will be no interaction between the Px and Py orbitals with this S orbital. In other words, those Px and Py orbitals will remain as non-bonding orbitals. When we study about the HF molecule, we will study about this little bit in detail. Next, we move on to P orbital overlap. Px and Py are perpendicular to Pz, so there will be no interaction. Next, we will move on to PP overlap. Although there is no reason why Px or Py cannot be used, most books will use Pz as the reference. Now, the head-on overlap of two Pz orbitals will result in the sigma bonding as shown here. Now, the minion asks the question, how P orbital overlap gives sigma bonds? My answer, there may be a misconception that for sigma bond formation we always need a S orbital, but that is not correct. S atomic orbital overlap always gives sigma bond. S and P atomic orbital overlap also gives sigma bond. By analogy, we expect P and P overlap also to give pi bonds. It is basically the way in which the atomic orbital overlap decides which type of bond that will be formed, and not based on what type of the atomic orbitals that are involved. So, the take home information will be, it does not matter whether it is SS overlap or SP overlap or PP overlap, the overlap actually decides what type of the bond formation, and we cannot think all the time PP overlap will lead to pi orbital and SP or SS orbital. So, the take home information will be the type of the orbital decides type of bond formation. Let us look into antibonding orbital. It is destructive overlap. We can say destructive overlap is subtraction. When two S orbitals destructively combine, we get the region of low electron density between the nuclei. Due to this, there is high in energy. If you look here, when S orbitals combine, the bonding leads to this type of arrangement. The antibonding orbitals leads to there is a place where 0 electron density is present. That means there is a node in between these two lobes. So, this is what is called the antibonding arrangements, and due to which this is having high energy. Similarly, the sp orbital overlap leads to bonding as shown here, and the antibonding orbitals are depicted as given here. And finally, when we talk about pp overlap, the pp overlap leads to bonding as shown here, and the antibonding orbitals are written here. So, if you look carefully in all the antibonding orbital, there is some region where we have 0 electron density. So, in other words, we can say the antibonding orbitals are actually having a nodal plane.